This is the last section in Chapter 3, so it's 3.5, Oblique Asymptotes. And up to this point, when we've talked about a function and its graph, we've identified certain characteristics. So you're very familiar with the y-intercept and how to plot a y-intercept, and also you should be familiar with how to find a y-intercept. You plug in f of 0 and that'll give you your y-intercept. We also talked about the x-intercepts, and that was the numerator in a polynomial. If you took that numerator and you set it equal to 0, that would give you the x-intercepts. And many times we gave you the numerator in factored format. So it would look something like x plus 2 and x minus 3 or something like that. So we started out with these two. And then we introduced you to vertical asymptotes. And we should say with the x-intercepts, you would plot, this was x equals -2 and positive 3. So you'd plot an x-intercept here and an x-intercept here. Then we talked about vertical asymptotes, and vertical asymptotes were what you obtained when you set the denominator equal to 0. So if the denominator in a rational function looks something like x plus 4 and x minus 1, you knew that you had vertical asymptotes at x equals -4 and x equals positive 1. So you would have vertical asymptotes here and here. And then yesterday we introduced you to one more type of asymptote. That was the horizontal asymptote. And when it came to the horizontal asymptote, there were basically three types. If the degree of the numerator was greater than the degree of the denominator. So we wrote it something kind of like this. If you had ax to the n divided by bx to the d, and the reason we used n and d was the numerator exponent and the denominator exponent. So we wrote something like this: if n was greater than d, then there was no asymptote, no horizontal asymptote. It didn't exist because the graph took off and went to infinity. It kind of went like that. So there was no horizontal asymptote. If n was less than d, then the horizontal asymptote was at y equals 0. And so this was a graph, it didn't go up to infinity like the first one. It came down from infinity and it approached the x-axis and it kind of hugged that x-axis. If it turned out that n was equal to d, then your horizontal asymptote was at the coordinate a over b, which came from the lead coefficients of the polynomials in each, the numerator and the denominator. And so that would look, something like this, and this would be y equals a over b. So that brings us pretty much up to speed for this whole chapter: y-intercepts, x-intercepts, vertical asymptotes, and horizontal asymptotes. Okay? And this last section, what we're going to talk about are oblique asymptotes. And when it comes to oblique asymptotes, oblique means not at a right angle to anything. So your horizontal and your vertical asymptotes are all at right angles to stuff. An oblique asymptote might look like this. And if you had a horizontal asymptote that looked like this, the graph of your function would be bound by both of those asymptotes. And so you might have a function that ends up looking like this. To get at this y equals mx plus b, we can no longer play with these really nice pre-factored numerators and denominators. Because when you have the really nice pre-factored numerators and denominators, you get vertical and horizontal asymptotes. So instead what we have to start playing with are things that look like this. So this is an example of a polynomial rational function that has an oblique asymptote. And we're going to figure out what that oblique asymptote is. you're going to look at the top and you're going to say, I can't factor that thing, and you're right. We're not going to factor the top. Instead, what we're going to do is we're going to divide these two. We're going to do polynomial division. And the way you do polynomial division is just like how you do long division. So you start by putting the numerator under a box. So we'll put 5x to the third minus 26x squared minus 69x plus 46. And then on the outside, we're going to put x minus 7. And now what we're going to do is we're going to focus solely on the x term out in front. And we're going to say, what do you multiply x by in order to get 5x to the third power? What do you have to multiply that by? And whatever that number is, it goes up top. So we're going to multiply everything by 5x squared. So we're going to take 5x squared and we're going to multiply it by x minus 7. And then we're going to write it down below. So when we do this multiplication, we're going to get 5x to the third minus 35x squared. And now we're going to subtract these. And one thing that I like to do, I like to put this whole thing in parentheses and a subtraction symbol out in front, just to remind me that I'm subtracting, and you'll see why in a little bit. So 5x to the third minus 5x to the third is 0. And that's anticipated, right? Like we wanted that to happen. We wanted those two to cancel out. But here's where things get tricky. A lot of students will look at the negative 26 and the negative 35, and they'll say, oh, well, that's negative 61x squared. But remember, you're subtracting these two quantities. 5x to the third minus 5x to the third. So you have to say negative 26x squared minus negative 35x squared, which makes this not a minus 35, but actually a plus 35. So now when you put these together, you'll get positive 9x squared. And then bring down the negative 69x. So now you do the same process. So what do I have to multiply the x by in order to get a 9x squared? Yeah, 9x. And so we'll put the 9x up top, up here. So we'll say plus 9x. And when we do this multiplication, we'll get 9x squared minus 63x. And now we subtract these. And again, I kind of like to put this in parentheses and put a minus out here to help me remember. Some students do this too. If you're not in with the parentheses, put a negative here and change the sign on the 63. That's another way to do it. You're doing the exact same thing. Either way, you want to change the signs and then add them together. So 9x squared minus 9x squared, this is gone, that's 0. And negative 69x plus 63x is negative 6x. And then bring down the 46. And then our last move is, what do you multiply x by to get negative 6x? I think that's a negative 6. So when we do this multiplication, we write it down here, and we'll write negative 6x plus 42. And now we want to subtract these, and you can do the sign change thing. So change the sign, change the sign. These cancel, and you're left with a positive 4. And that's your remainder. You have a remainder of 4. So the answer to this, when you divide these out, it's going to be 5x squared plus 9x minus 6 with a remainder of 4. And the interesting thing is that this guy right here, the answer that you get when you divide these out, this is your oblique asymptote. This asymptote happens to be a parabola. It's not an actual line. That's what the equation looks like. When you take this function, 5x to the third minus 26x squared minus 69x plus 46 all divided by x minus 7, and you graph it, you get this. Now, isn't that interesting? It almost looks like a parabola, but it's not. It's kind of goofy over in this region right here. If we were to graph our oblique asymptote, look at that. So I don't know if you can see it. Let's see if we can zoom in on this guy. I'm just going to zoom in on this window right here. You see that asymptote? How the graph approaches it, but it never crosses it? That's an oblique asymptote. This is actually a parabolic asymptote, which is pretty cool. So this graph comes along and hugs the asymptote right up until it hits the vertical asymptote. And remember, if you go back to the function, it still has a vertical asymptote. Where's the vertical asymptote? Look at the denominator. 7, right? There's a vertical asymptote at 7. Look at the graph. Vertical asymptote at 7, right here. But then there's also an oblique asymptote. Let's try this one. So again, we're going to go through this division of polynomials. So in the box, we'll put 12x to the third plus 64x squared plus 92x plus 28. And outside, we'll put a 4x plus 12. And now, your focus is on just that lead term, that 4x. What do you have to multiply 4x by to get 12x to the third power? So I think we need a 3, and I think we need an x squared. So now take 3x squared and multiply it by this whole thing. So we'll end up with 12x to the third, which we anticipate, plus 36x squared. And now you're going to subtract these two. So these go away, and when you subtract this, we'll borrow one from there, and we'll get a 28x squared. Bring down the 92x. And now you do the same thing. You say, what do I multiply 4x by to get 28x squared? And I think that'll be 7x. So again, we do the multiplication. We're going to write it down here. So when we multiply, we'll get 28x squared plus 84x. Then you subtract. These are gone. And you get, what is that, 8x. Bring down the 28. And then one more time. What do you multiply 4x by to get 8x? I think that's a 2. So when you do the multiplication, you get 8x plus 24. Subtract, and again you get a remainder of 4. And this guy, this is our oblique asymptote. Let's go to the graph. Do this problem off to the side, and then go back and fill in the blanks later, because it's kind of tough to fill in the blanks and try to solve the problem as you go along. So what you're going to do is you're going to put 4x to the third plus 2x squared minus x plus 1 under the division sign. And then you're going to put an x minus 2 out in front. And now we're going to go through and divide this all out. So you're going to type all of these into the appropriate box. And then plug them in. And so we're going to do the exact same process that we did before, but this time it'll be a little bit easier. So in the box, we're going to put 8x squared minus 10x minus 1, and we'll put 2x minus 3 on the outside. And once again, don't forget, this 4x plus 1, that is your oblique asymptote. The homework problems call it a slant asymptote. Taking a look at the first problem, the equation of the vertical, or the first part of the problem, where do you find the vertical asymptote information? Right here in the denominator. So this function has a vertical asymptote at x equals 3/2. You take this guy and you set it equal to 0. 2x minus 3 equals 0, 2x equals 3, x equals 3 divided by 2. So that's where your vertical asymptote is. So if we were to sketch this, we have a vertical asymptote at about 1.5. Something like this. Our oblique asymptote is at 4x plus 1. And you know what 4x plus 1 looks like. It's a line. It has a y-intercept at 1 and a slope of 4. 1, 2, 3, 4 up and 1 to the right. So this is going to have an oblique asymptote that looks like this. And if you don't mind, I'm going to scale this a little bit. I'm going to tweak the scale, and I'm going to really make it look like this. I know this isn't what the graph looks like on a square scale, but it's how I can get it to fit into the frame. And now the graph is going to look something like this. That's what the graph should look like. We have a vertical asymptote at 3/2, and then an oblique asymptote, and those two together kind of fence in this function. There it is. So here's your vertical asymptote at 1.5, running right along here. And then there's an oblique asymptote at, what was it, 4x plus 1? There it is, 4x plus 1. And you can see how the function gets close to 4x plus 1, but never quite crosses it. One more, just for kicks. So we're going to do the exact same thing. So we've got 40x squared plus 63x plus 22, and we're going to divide that whole thing by 8x plus 3. This is the oblique asymptote, 5x plus 6. The vertical asymptote is at negative 3/8. That comes from here. 8x plus 3 equals 0. 8x equals negative 3. X equals negative 3/8. And so do we have enough information to graph it? Yeah, I think so. Vertical asymptote at negative 3/8, which is probably something like this. Oblique asymptote with a y-intercept at 6, and again this is not drawn to scale, it's just drawn to illustrate, something like this. Whoops. Make this a dotted line. And then we're going to have a function that probably looks something like this, and something like this. And there it is.